Okay, so there may be some hissing sound in the background when some of these records because I have to run a fan. It's very hot. Mumbai is very hot. March, April, May are a torture, and I don't run the AC. So we are discussing grasping complexity and we are looking at intrinsic volatility. I had stopped in the middle because I had to run off to a meeting. So we had already read this Perot's thing about the nuclear accident, and we have talked about the examples with the stock market crash, and I had mentioned how stock market crash is complicated also because there's a lot of uh, mental models of people, investors, let's say, are involved because they are not necessarily responding to data that is in front of them. They are responding to rumors that COVID may do something, that China may have a serious problem, it may affect supply chains, it may affect stock markets and economic activities and so on. So markets can crash, and then irrational exuberance dominates, so you recovered to well beyond what was happening before COVID, and many retirement accounts grew nicely and then they have flattened or even gone down a little bit and so on. So volatility is an intrinsic part of complex systems, but when we are talking about human environment systems, we are also adding human behavior into them, and the question is how to represent those when we want to worry about sustainability, right? So I think I stopped here, so let's continue here in terms of intrinsic volatility. No matter how hard we try to grasp and address this kind of destructive event, whether it's a nuclear accident or a black swan event on the stock market, we often make the wrong diagnosis and may even aggravate the problem by trying to solve it. When we encounter a problem in a complex system, we regularly rely on active and often automatic technological devices to address it. For instance, when we want a more aesthetically pleasing grand lecture hall for 1200 people with combustible wood on the walls and ceiling, we install a sprinkler system and a fire alarm and count on these installations to work. So here is the lecture hall being discussed. So there are many ideas out there in terms of reducing the use of cement and steel for building structures, that wood can work very well even for a high rise. Can you imagine? China has built some demonstrations of high rises built with woods, and there are fire retardants put on them and so on, but the main idea is that they not only reduce emissions from cement and steel, which also use a lot of energy, but also they lock up the carbon. So you are growing trees and you are capturing carbon and you are locking it up in a building. That's the idea. So all these backup systems are then needed in terms of making sure it doesn't burn down very quickly. So you need fire alarm, sprinkler systems. If not, it would most likely lead to a disaster. Similarly, the Boeing 737 MAX flight stability problem was addressed by installing a maneuvering characteristic augmentation system (MCAS), which led to two fatal crashes when malfunctioning. What is supposed to be a very safe protective device to deal with human errors actually ended up malfunctioning itself, and then humans couldn't control the plane, so it just crashed. So imagine how complex the safety system there is, that you don't even have a control. Relying on such technological solutions is not only demanding that everything works all the time, it also increases the system's complexity, which can increase its catastrophic potential through additional combinations of failures or overriding better human decisions when the system decides something is wrong. Regardless of how improbable these disasters are, the additional combinations of failures increase their probabilities of occurring. This relationship between complexity and disaster explains why the overall process of increasing complexity is problematic. So we have seen this in chapter 6. when we talked about these things. So relying on such technological solutions is not only demanding that everything works all the time, it also increases systems complexity, which can increase its catastrophic potential through additional combinations of failure from Perot 1984. This is the example we just mentioned. So instead, what Perot also says is, instead of further increasing the complexity of already complex systems, we need to reduce their complexity through increasing modularity. So designing with modularity is become very common now, even for apps. For example, we used this example somewhere before, where you don't need to start from scratch. Let's say you're inventing something and you want to build an app and make money on it, obviously, but you don't need to start from scratch, because there are bits and pieces of the software system that goes into an app that you can borrow. There are patent issues, IP issues, you have to share royalties, this and that. But increasing modularity also reduces these cascading effects and catastrophic failures. So modularization is about removing, or at least relaxing, dependencies between parts of a system, so one module can fail without cascading into all of the system. It's important to note that this may only work if removing the actual dependence, not merely ignoring it, which unfortunately is rather common when governing complex systems, and there are many good examples given here. So I've mentioned already several times that tipping points are tricky because they are obviously they exist in the system, and then there are ideas of social tipping points. People like Malcolm Gladwell talk about it, that people keep on moving in one direction and then you reach some critical threshold beyond which the system goes into a new equilibrium or a new state. And in the Earth system, many tipping points are argued, but predicting them is not possible with models. By definition, tipping points are not really predictable, so it then comes down to how to prepare for them and how to at least have an idea of where they may be. If you say the system is complex and emergent, then obviously you don't necessarily have an idea of all the tipping points, and catastrophic failure that we just talked about is just one example of that. Nonetheless, tipping points are complex systems, parts of the complex systems that not only exhibit disproportionality between cause and effect, but the relationship between cause and effect may also change drastically over a certain level as a result of rebalancing of interlocking, reinforcing and balancing feedback loops. Sounds complicated, but basically if you have increasing greenhouse gases, increasing temperatures, increasing humidity, further increasing warming is a positive feedback, and that begins to lead to melting of glaciers, which reduces reflection of sunlight, that further amplifies the warming, and so on and so forth. So you can have a quick explosion or amplification of an initial perturbation that may completely push you into a new state beyond a certain level of growth of the initial perturbation. It means that complex systems can have thresholds over which they suddenly shift to a completely different regime of states. This consequence of complexity is called tipping points. Gladwell, as I mentioned, has written about it, and they constitute tipping points constitutes a challenge for understanding and explaining phenomena and improving problems in complex systems. Of course, there is the idea of trying to forecast them as well, so that you can be prepared, but better to accept that they are not really predictable. Tipping points are especially central to the multi-equilibrium approaches to resilience that we mentioned in chapter 7, where resilience is defined as the system's capacity to avoid tipping points. So it was not only about coming back from the detours onto the sustainable pathway, but also trying to avoid tipping points somehow. However, tipping points are also consequential to the approach of this book, since they bring human environment systems into fundamentally different regimes of states, altering their capacities to continuously develop along their preferred expected trajectories, whilst remaining within human and environmental boundaries. Okay, so let's look at the props used. Here is 9.16 tipping point just ahead. So you are driving along and you either Google misled you, which has happened, or you just didn't pay attention, and there you are tipping over into a water body, and that can be disastrous, right? So here is 917, a compost approaching the rate dependent tipping point of catching fire due to escalating internal heat release by organisms respiring organic matter. There is a lot of examples from peatlands burning. Smoldering fires can go on for a long time, and then they can become a problem. Of course, they also release a lot of the locked up carbon from peatlands and so on and so forth. So examples as such exist. The last general type of tipping points, I'll just read it just because we want to look at this figure of 917. Did I finish this? Yeah. Oops. Okay, so this consequence of, I read this. Yeah. The last general type of tipping points is commonly referred to as rate dependent. So how quickly you move towards one direction can take you over the safe tipping point and put you into a new regime, which we will look at again in terms of the smoldering fire. And this also is applied often to the way we are emitting greenhouse gases and the rate of warming that's happening. You know, language like the sixth extinction come from there, where things are changing so fast, the velocity of change is so fast that many species cannot really keep up. So the mobile generalists can move to a safer temperature or rainfall and so on, but some species who are sedentary specialists cannot move when things change very fast, so they just go extinct. So those are kind of tipping points, because extinction of one species may lead to cascading effects. If bees disappear, then what happens to crop yields and vegetation and biodiversity and so on. Okay, so those are the kind of things. It comprises, so tipping points with rate dependent tipping points comprises tipping points driven neither by steady state change, so bifurcation type, nor short-term variability, so noise induced perturbation. They're instead driven by the rate of change exceeding some threshold over which the runaway change occurs, which is what we looked at here. Tim Lenton writes a lot about this, but this is a culture in Europe, and US is not really so excited about tipping points, and I am also not a big fan of the way it is stated that we are closer than we think to the tipping points. What does that mean? It's not very scientific, if you ask me. In other words, the rate of change is so fast that the system cannot absorb it to stay in its current regime of states. Rate-dependent tipping points were initially believed not to have the same early indicators as the bifurcation type. However, research now suggests that increases in both variance and autocorrelation may be observed as the system approaches the threshold rate before tipping, although with substantially different delays for different levels of noise that initiate the rate dependent change. You can use many examples here. One thing is to be able to have early warning so that you are ready. So let's say the volcano in Iceland is producing a lot of tremors, which can be seen in the seismographs, so you know it is getting ready, but you cannot say exactly when it will explode or how strong it will be. And it's a question of how do you prepare for it. Do you evacuate everybody? And how far do you go in evacuating people? Just close to the volcano or very far away? How far away? So what happens even if you can expect or anticipate a tipping point, or how to deal with it, is still a very, very difficult problem. Nonetheless, knowing them and knowing the early warnings is always useful, right? So I will leave this podcast here. We'll come back and wrap up Grasping Complexity by reading off some conclusions, which is 4 slides, but that should be okay depending on how much time I will take discussing it. Okay, see you in the next podcast and the last podcast of this chapter on Grasping Complexity, and then we will go to Governing and Governmentalization, which is also a new chapter in the second edition. Okay.